Hi, I'm Austin Eichelberg and this is ME62, Nonlinear Waves through Granular Media. Granular media is a type of material made up of many discrete solid particles. The many local interactions between particles in these materials make them especially useful for studying waves and vibrations. Nonlinear media has a vast array of useful applications, such as shockwave insulation, energy absorption, and waveguiding. The specific objective of my research for senior design is to create a type of material structure which allows waves to pass through in only one direction. This is known as non-reciprocity. You can see in the example how solitary waves moving in the forward direction can pass through the material without any loss in amplitude. However, the waves that enter in the backward direction begin to immediately die out. To create my granular media, I use in-plane disk magnets with their poles facing in the same direction. This creates a repulsive force between them, which is a function of their separation distance r. You can notice how the r in the equation has an exponent of -4. While keeping all other variables constant, it can be shown that the stiffness between magnets is highly nonlinear. To give the magnet disks the freedom to interact with each other, they are placed on an air bearing which floats them. Each magnet disk is composed of 3 parts: the permanent magnet, the plastic disk, and a glass cover slide for frictionless motion on the air-bearing surface. To start off, I consider what will be the most basic building block of my material. This is a unit cell, a magnet disk which is bounded by the potential energy of magnets embedded into a fixed rigid boundary. Here you can see how the magnet disk automatically finds its lowest potential. For my boundary, I use 2 layers of different size magnets. One of them is 3mm by 3mm, the other 2mm by 1mm. Here, the magnets are aligned. When I overlay the potential energy of the x direction, you can see that the unit cell has only one potential well. By shifting the outer boundary along the horizontal, I can divide the unit cell into 2 potential wells. This is known as bistability. This will make it so that pushing an element in the forward direction will take only a small amount of energy, while pushing it in the backward direction will take a lot. Adjusting the vertical spacing of the boundary allows me to change the relative height of each peak. This can make it easier or harder for the disk to change potential wells. To summarize my design, the inside boundary of magnets will be shifted a certain amount to create bistability. Disks will be added to the system so that when energy is added to one of them, the wave can propagate throughout. I numerically integrate the equations of motion to simulate the material dynamics and test for working geometry. To do this, I use the Verlet integration method, which is a useful method for keeping the total energy of the system constant between time steps. After finding a working geometry, I fabricate my boundary by laser cutting it out of a solid piece of plastic. My first experiment goes well, the wave moves in the forward direction, but I notice that it bounces off the back of the boundary. In the reverse direction, the wave appears to slow down, but it does not die out before reaching the other end of the material. To improve upon my original design, I decide to use the circumference of the air bearing instead of the diameter. This is to add more unit cells to the system and remove the unwanted boundary effect. Before making the ring, I first improve upon my unit cell design so that the wave in the backward direction is stopped almost immediately. Still, the wave moves fine in the forward direction. Next, I test that the wave can move around a curve without stopping. And finally, I make the full ring and test it in the forward direction. and in the reverse direction. To summarize my work this past year, I developed an experimental setup for nonlinear elements. I tested my system numerically, and I successfully created an experimental design which worked. Moving forward with my research, I plan to add the ability to quickly and easily reset the boundary, change the direction of non-reciprocity, and finally develop the system to work in 2 dimensions.